In today's lecture, we will finish the topic about pressure sensors. And since this will be only for about half an hour, we will start the new topic, which will be flow sensors. So let's take a look on this. Deformation sensors are used typically in industrial systems simply because the calibration instruments for pressure are very sensitive to vibrations, to dirt and so on. So they are used in labs to calibrate the instruments. So last week we have discussed the calibration instruments, and today we will take a look on the industrial versions of pressure gauges. First of all, we need to know that we will transfer the pressure that we measure to a deformation of some element. So this is not directly the definition of pressure. So we cannot use this for primary calibration to calibrate all the other instruments. But anyway, the accuracy of this deformation manometers may be quite high as well. I will first show you some basic, let's say, mechanical pressure gauges, and then we'll see inside of one of the industrial smart pressure sensors used today, and we'll see how it is working inside. So let's start with the Bourdon element. The Bourdon element is an important component of a pressure gauge, and it is based on deformation. The Bourdon element is a tube that typically has this shape, like this. This is the cross section. So it is a tube that is flat, and then the tube is bent in a spiral. So it typically looks like this. It does not need to be an entire spiral like this. It can be just a semi-arc, for example. This Bourdon element is closed at one end. So at this end the Bourdon tube is closed, and this end is connected mechanically to a system of transmissions. So this may be like a lever system. Here you see one lever and a second lever here. It's a simple example. On the next slide we'll see the real instrument. And this mechanical transmission changes the motion of the Bourdon tube into the motion of the needle. So this here we have the scale, and on the scale we can read the pressure. So the gauge is calibrated in pressure. On this end we have an opening to the Bourdon tube, so we can connect the pressure P that we want to measure. And if this pressure P is increasing, this Bourdon tube is trying to straighten itself, so the end of the Bourdon tube is moving like this. So this is this dotted spiral that we see here, and as this end is moving, this motion of the Bourdon tube is transferred through the levers to the scale, and we will see a change. Now there is a very good video about how this is produced, so I recommend you to take a look on this link where you can actually see the production of such Bourdon tubes and also the functions of the lever system and of the whole instrument. Now the tube is made from different materials, and the material is selected based on the pressure range. So for relatively lower pressures, the Bourdon element is made from brass or bronze, and for high pressures it is made from steel. Now let's take a look on how this looks like. So this here is the Bourdon tube itself, just the Bourdon tube without the ends. So it initially starts like a tube that is flattened, and then during the assembly process they solder to one end the lever system and to the other end the input port for the pressure gauge. So this is the pressure Bourdon tube, and here we see a Bourdon tube inside of the instrument. Now this instrument is a little bit special because it has two Bourdon tubes. This is an instrument to measure differential pressure. But anyway, here you can see that this end, this is the sealed end here, and this one here. And through those levers it is connected to the needle. And here we see those gears that transfer the actual motion to rotation of the needle. And here the second end of the Bourdon tube is soldered to this fixture, and this is the input port for the pressure sensing. Here on this picture you can see just one Bourdon tube, so this is a pressure gauge to measure one pressure. And again, here this is the input port, this is the Bourdon tube, and this is the sealed end, and through this lever and this lever and this gear the motion is transferred to the gear. So when you increase the pressure that you have inside, now this Bourdon tube tries to flatten itself, so it tries to move like this upwards in this picture, and then this motion is visible on the needle. Here on this picture on top left you have the whole instrument. So here is the needle, we have the scale, and behind the scale there is this mechanism with the Bourdon tube. Now typically the Bourdon pressure gauges, they do not have any electrical output. So you mount the instrument in your application, you locally read the pressure, and you don't have any electrical output. Of course, it could be equipped with an electrical output. You could sense the angle of the needle, you could have any kind of position sensor mounted on there, but it's not very typical to find Bourdon elements with an electrical output. The Bourdon gauges are very robust, so they can work with environments where you have vibrations, where you have changes of temperature. So they are very common in many industrial applications, but as I said, they are not connected to any control system. The accuracy class is typically above 1%, so it's not the most accurate pressure gauge, but if you just want to read the pressure somewhere in your application, now this is quite sufficient. Let's take a look on something a little bit different, although the principle is quite similar. And we will slowly move to sensors with electrical output. So we want to connect our sensor to some control system so that we can sense the pressure somewhere and use it for control. Now what you see here on this picture is the principle of basically all pressure gauges that you can find today, and they have the electrical output. Here we can see a diaphragm, and in this picture it is shown like a diaphragm that is on a chip, but it can be also a diaphragm made from stainless steel, made from brass, made from copper, and then you can have normal force sensors, so strain gauges mounted on the diaphragm. So here the diaphragm is deformed when we apply some pressure. So what we see here on this picture is an example of an absolute pressure sensor. So here we have some reference pressure, and here is the pressure that we want to measure. Now if this pressure P is larger than the reference pressure, then the diaphragm will bend like this, and this bending is measured by strain gauges. Here it's shown like a chip sensor, so it's equipped with piezoresistors, but nothing prevents you to make a diaphragm from any other material and place normal strain gauges on it, as we've seen in the lecture about force sensors. Now of course in this picture this bending is exaggerated, so the real bending is not as big as we see here, but it's small but still possible to measure. Now those sensors, those strain gauges are typically connected in a bridge circuit. So we have discussed bridge circuits when we've been talking about force sensors. So here is the schematic. So we have 4 sensors like this. You can see that 2 of them are measuring compression. So R1 and R2 in this case measures compression, and R4 and R3 measures tension. So we can read the output voltage, which is a function of the deformation. And this principle is basically used in all today's pressure gauges with electrical output. Some of them have a diaphragm, some of them have a little bit different configuration, but in all cases we measure the deformation of something. Here is another example of exactly the same principle. Here we see that this is a diaphragm. The measured pressure is connected from the left, so there would be an input port. And here on the right we have a set of electrodes. And as this diaphragm changes its shape, so if we apply more pressure P1, then it gets deformed like this. And it will move this rod, and this will move the electrodes. Now one set of electrodes, the one on the right, is fixed to the frame, and the other one, the one on the left, is fixed to the rod. So when this rod is moving, then we have a change of capacity that we may detect here. So again, we measure the deformation of the diaphragm, but in this case we sense the changes of capacity, not the deformation directly with some strain gauge. And this principle is very common in today's industrial sensors that are called smart sensors. Here you see few examples. Some of those sensors, the ones here and here, are typically used in the automotive industry, for example, to sense the pressure in a tire of a car that you may have. The ones here on the right, that's a sensor used in industrial applications. Now the principle is the same. They typically work with capacitive changes, as we've seen on the previous picture. The difference is in the input ports. Here this input port and this input port in this case opens to ambient, so it measures the pressure that you have in the air, or if you have some in some tire or in some box where you want to measure it. And here in this case you have this input port, this thread, and you connect the sensor using this thread to the sensor. Typically the accuracy is about 1, maybe 1.5%. So it's about the same accuracy as the Bourdon tube, but in this case we have an electrical output. Now what you see here are the insides of such a smart sensor. So the sensor looks like this. They have a typical shape, so this is the input port. Here typically in this part there is the diaphragm and the first electronic circuit that senses the deformation of the diaphragm, and here in this part there is the electronic circuit that provides some outputs. So you may have some display, you may have some current output, you may have some data communication. And inside of this is such a circuit that looks like this. Here we can see the diaphragm. So this is changing its shape when we apply the pressure. This is the rod that moves left and right as the diaphragm is changing. And here this is the set of the electrodes. So you can see that this is the fixed electrode fixed to the frame in here, and this is the movable electrode, and this moves left and right. So as you apply pressure on the diaphragm, now this moves to the left, it moves more into the capacitor, and hence we have an increase in capacity. Now this is a connector that connects this assembly electrically to the electronic circuit that is here. And this electronic circuit provides you, for example, current output that you may connect to a controller system. So it may be produced like this, like an industrial device with those input ports, or it may be produced like a chip. And then this chip may be used in a tire. It may be also used as a barometric sensor, for example, to detect the altitude above sea level in a plane, for example. Now here is such an example. It's still the capacitive sensor for pressure, but now it's produced on a chip. So I've found here two versions that we can discuss. The one on the left, it has a round diaphragm, so we can see the diaphragm over here. You can see the scale, so this is 75 micrometers, so it can be very small. The size of the chip is typically something like 5 by 5 millimeters, approximately, including the terminals. And here we can see the view when you cut through the material. And we can see that here this is the diaphragm itself. This is the hole under the diaphragm, so the diaphragm is changing its shape like this. You can see it here. This is the sealed edge of the diaphragm, and this is the cavity under it. And we can evaluate by capacitive changes or by installing strain gauges on the diaphragm the actual pressure that we measure. The picture on the right is very similar. The difference here is that the diaphragm here is rectangular. It's a little bit bigger. Here they have 1 millimeter approximately square, but it works also in exactly the same principle. We can see here that we have a platinum piece, so this acts like a temperature sensor. So in many cases, the pressure sensors that have a digital output on a digital bus, they have also the ability to give you temperature as well. The reason is simple. Typically, or one of the applications of those sensors is also to measure the altitude above sea level. For example, if you have some control system for a hobby airplane or something like this, then you want to know what is the altitude, and it can be calculated by using pressure, some pressure reference, and temperature changes. So you can typically read through a digital bus directly the info about temperature and pressure. In some cases it provides you also the altitude directly, like above sea level, if you give the reference pressure. And now at the end, let me compare different pressure gauges. We have seen only some of them that are here in the table. We have seen the Bourdon element here today. So typically this is the pressure where it can work. So it can work for larger pressures. So if you are looking for something like 10 kilopascals or 1 megapascal, then the Bourdon element is a good choice if you don't need an electrical output. And the diaphragm type can typically measure to lower pressures. So here you can see approximately the estimate 10 to the power of minus 2. This is like a typical range. So here in this range we may expect the diaphragm to work. We have discussed also some other types, like for example the liquid manometer. We've discussed that last week, so this is approximately the same range like the diaphragm. It's not very suitable for higher pressures because of the column of the liquid that you read, but it is quite suitable to read with good accuracy the lower pressures here in this range. And today we have discussed also the capacitive diaphragm, which is here, and it can work up to, let's say, 10 to the power of minus 5. So smaller pressures are possible if you compare that to the Bourdon element, for example. Now, we did not discuss the principles shown here in the bottom. Those are specialized pressure gauges used for very low pressures. For example, here you can see 10 to the power of minus 12. So those are called vacuum gauges. We'll not discuss that. It's just to show you that not every principle is suitable for the whole range of pressures. So for some pressures you need to use the Bourdon element, for some lower pressures you need to use the capacitive diaphragm, and so on and so on. Okay, at the end, let me discuss how to correctly install pressure sensors in some application, because it's quite important to install the sensor correctly. If you do not install the sensor correctly, it will measure something, but it may not be necessarily what you need to measure. So the first problem might be caused by anything that can change the actual pressure. You can imagine that it could be a valve, it could be a flap, it could be a bending like this, and anything that changes the pressure will actually have an influence on your measurement. So there is a rule how far should your pressure gauge be installed from those elements. So let's take a look on that. We need to keep this distance to be at least 10 times the pipe diameter, and this applies for clean liquids. So if we want to measure the pressure, let's say here we have a pipe and I want to measure the pressure of some fluid in this pipe, I will attach the probe in this place. So anything before and after the flow, such as a valve or bending, could have an effect on the pressure that I measure. So the recommended distance is at least 10 times pipe diameter. Then the recommended diameter for this pressure tap is about 1 millimeter. And again, this applies only for clean liquids, for clean mediums. Of course, if you have some particles in there, now this might be too small, and you may block this opening with some dirt, for example. Then this goes to the pressure sensor itself. But this pressure sensor is not connected directly to this opening, but we use some valves to allow the connection and disconnection of the instrument. So typically it looks like this. Here is the probe where we have the sensor attached. Then we have some piping that goes to the pressure gauge. So this is my pressure gauge. And typically this connection is made with a pipe of a diameter between 6 and 10 millimeters. Now you can install anywhere you like this instrument, but you need to keep the following rules. Now it's important to make an inclination here on this pipe. This inclination is typically about 1 to 20 ratio. And here on the highest place on this system, you need to place a valve where you can escape the air. Eventually, if this is a liquid, for example, then there might be bubbles, and with those bubbles will fill this system. Then you will have bubbles at the highest place, and your gauge will not measure properly. So this is the air escape valve. Now this valve is used to disconnect this whole system from this probe. So this valve is either fully open or fully closed, nothing in between. So it does not have an effect on the pressure because it's fully open. And here on this position, the lowest position, you should have a valve that allows you to drain any impurities. So if you need to remove these impurities, they will accumulate at the lowest position because they are the heaviest. They will accumulate here, and from time to time you will open this valve, you will drain those impurities, and you will clean the system like this. So now those rules applies for clean mediums. If we are talking about hot vapors, we need to cool down the vapor before we connect that directly to the pressure gauge. So now this can be done in two ways. If it's a horizontal pipe, we have this probe like we've seen before, but now here we add something that's called a vapor condensation loop. And this vapor condensation loop is a loop like this of the pipe, and in this loop we give the liquid enough time to cool down, and only then it's connected to the pressure sensor. So again, here there is a valve, and we might have additional valves in the system, but this valve serves to disconnect again the instrument from this condensation loop and from the probe attachment. It works in the same way also if you have a vertical pipe. So here is the vertical pipe, probe where it's attached. Here is the vapor condensation loop. So here the medium that you measure will cool down, and here we'll have lower temperatures and we may connect the pressure sensor. And the last problem might be with the aggressive liquids or gases. So if your liquid or gas might damage your instrument, you need to separate it from the measured liquid. Now what you see here on the screen, this works only if the measured liquid and the separation liquid, they do not mix together. If they mix, you need to use, for example, a diaphragm. The picture on the right shows the installation where the density of the measured aggressive liquid is actually higher than the density of the separation liquid. So for example, this could be, let's say, an acid, and this could be, for example, oil. So the separation liquid is some liquid that fills the entire system of the instrument from this separation tank to the sensor, and it's not aggressive. And in this case, it's in direct contact with the aggressive liquid, but since they do not mix together, we don't need to put any diaphragm. If they mix together, what you need to do is you simply install a diaphragm in here, and then this diaphragm changes the shape, goes like this or goes like that, based on the changes of actual pressure in the measured liquid. Now in this case, the assumption is that the density of the measured liquid is always higher, so it stays in the bottom. So here is the probe where you measure, where you tap your pipe of the liquid, and the pressure sensor needs to be always above, so that this whole system is filled at all times with the separation liquid. Now in the second case, as you see here on the left, the separation liquid actually has a higher density than the aggressive liquid, and therefore this pressure gauge is installed on the bottom and the measured liquid is on the top. Now if this is not valid, this assumption, if for example the densities change so that it may be for one temperature this case and for another temperature this case, then you need to use the diaphragm as I've shown you here in this example. Now the most common separation liquids are water, oil and air. So let's take a look on how to use water or air as a separation liquid. Here is an example how you can do it in a pipe. So here we have the pipe with the measured medium. We assume that we may add some water in the medium. So if this is some gas, it's possible for technological reasons to add some water like this. And at the same time, we want to protect this whole system of the instrument from the damage caused by the medium. So this will not be damaged by the gas that we have here. So here this whole system is filled with water. So we need pressurized water. This valve and this valve serves us to disconnect the water and the system, and this valve allows us to disconnect the pressure gauge. But here we feed some pressure water. It leaks a little bit in the pipe, but this whole system is filled at all times. So if this pressure is changing, it will be transferred through the water column here to the gauge, and we will be able to measure the pressure in the pipe. Now note here that this is tapped from the bottom side of the pipe, so that at all times we have water, and eventual bubbles that we may have here in the water may escape like this freely into the pipe. Now if you use air, the installation is almost the same, with one exception over here. The exception is that here, in the case of a gas, it's actually going from the top of the pipe, so that if there are some sediments and impurities here, they will not enter into this system. So again, this system is filled with pressurized air. The air is blowing constantly with some given flow. It's going into the pipe, and this whole system is filled with air. And again, if this pressure is changing, it gets transferred through this system into the gauge, and we can measure this actually.